Swayam Prabha. Digital India. Educated India.
So, when we discuss about Higgs, actually the purpose was to find where does this mass come from. Whenever we say mass, we have some clarity that we should see something, right? Yes or no? So, whatever we see around us, even through the universe, that is called visible matter. Visible, I can see, star, I can see. So, if we believe what we discuss about this Big Bang, and initially if there was something which, let's say, one bucket of energy was there, whatever was there, that's converted, and this bucket should be, today also that bucket should be there, because conservation of energy, mass, whatever you say, should be there. But when I see, actually I only see 5% of the bucket. What happened to 95% of this? Now everybody is surprised. It's only 5%, whole universe, what we see, star, galaxy, everything together makes only 5% of what initially we had actually. This is called, when that expansion happened, there is a part which is called visible matter, which is only 5%, and we are crazy about to understand where this 5% come from. Then you question is what happened to that 95%. This is what, if you look at the, you are trying to understand this, and this is the book you really have to read. By going to Higgs, even if we discover Higgs, that means we only understand the 5% which is only visible matter. For you, there are 95% books remaining, which student like you should come and get the courage to open one of the book. Okay, not your notebook, this book. So we didn't finish everything. We kept 95% for next generation to come and challenge the present generation. That is why I am here to talk to you early on. You are just 12th standard, you are learning what is future. When I was in 12th standard, I didn't know what my future is. You see, it becomes so competitive, challenging problem. We have to start early. Okay, so don't think that physics is done for you. 95%, and all of you may not dare to touch also. If somebody wants, he can come and touch this part. This is what we call dark energy and dark matter. I know, actually, ask question. This is my last class, okay?
Yeah. How do we know we only know 5%?
I see, actually. I know the conservation. Okay?
Sir, do we have any idea about what dark matter or energy is?
I don't
Not
talk.
even one idea.
No, I don't want to tell. I said this is for you. I am here to tell you visible matter. See, my focus is to tell you how I understand visible matter. That might excite you to read this book. Okay? I can talk about, but then I will be deviating from my deliverable to you. I will not even go to the half of thing. I say, sir, started something, didn't finish, start after. So we have to see how do we go about understanding this actually, how do we understand this also. That's kind of a roadmap for you. If you want to go to an unknown territory, how do you go about? When we did not know Higgs, how do we discover Higgs? I was like you as a student also, we never know actually anything. Now I am standing here, okay, we discover Higgs. Maybe some of you will be after 20 years standing with your junior saying that, yeah, I learned from there and then it helps me to go to unknown territory. Unknown territory means you have no idea what is there. Then you have to hit your brain to think, I have to think what is there. It's not easy. It is not reading a book. It is not Google search. It is searching your brain. Your brain is also a computer. Okay? Whatever you want to write, you have to write. It is capable of doing so many things. But we underestimate that. We only know if I can copy here, put somewhere else, I am a smart guy. That's not correct. Okay? So, we can discuss dark matter later, okay? It's fine, but it's there, okay? How do you find Higgs? If I go back 30 years back, 40 years back, everybody in the world was searching for Higgs. Then question, how do you find Higgs? Just like you will be, he is asking, sir, what is dark matter? You see, it's exactly same question was asked maybe 40 years back, like student like you. How to find Higgs? Where to find Higgs? This is the journey I am going to tell you, so that it will help you to understand how do you go to the unknown territory. Okay? How exciting it is, how challenging it is, how you should be ready for, you should not be scared. Right? Let's see. Why we need to do this? Because anything you do, yesterday I told, you have to have a plan, execution. Result may come, may not come. Result is the end product. And if you do everything correctly, you will be assured of your result. Okay, first thing is think positive and see that you have your roadmap. To find Higgs, we need accelerator, we need detector, we need theory. Three things we need. Theoretical physics is important. I am an experimentalist, but you see it says we need theory. Okay? Theory tells you where to look for. It just gives a direction, doesn't tell you, you may find it, but you can go, if you don't find, another direction. But finding job is for a experimentalist to find. You should be ready to go, and you may not be sure to find actually. So you should have courage to come back and start again new experiment. Okay? Why do we need Large Hadron Collider? I will discuss actually. Now you ask me, what is dark matter? I can tell you, that is where you will stop actually. I don't want to stop there actually. I want you to think, okay? Why do we need a detector? What does the detector do? What does the detector do? Detects what? Particle. Higgs is there or not, I don't know, na? Yesterday I asked you, you said electron, proton, that is a particle. My detector will detect a particle which I know actually. I don't know whether Higgs exists or not, right? So it will detect particle like electron, proton, okay, muon, pion, whatever. It's fine? Yes or no? Have you seen any detector? Anybody has seen the detector? Anybody? Huh? Metal detector does what? Detect metal. Do you have a particle detector? Have you seen any particle detector? Yes, he says yes. Have you seen that? Actual one. Real. Not fake one. No picture. Actual one. Seen? You have seen actually. Why me? Nobody says I am part of the group. Anybody says? Raise your hand who has seen. Yeah, he has seen. Yes.
Photodiodes. Photodiodes.
You see, photodiode he has seen. You see? I say, what is photodiode? Can you show people photodiode here? You have one photodiode? Which one? This camera I cannot see. Do you have a camera? You have a camera. That's a detector, photo detector. Photon detection is done by eye. Eye is a detector. So everybody has a detector. Nature has given you a particle detector. Okay? It's fine. You don't have to go to photo. Okay? This is photon detector, right? Eye is a detector, is a photon detector. Photodiode comes, it's an eye actually, sensing the photon. So everybody is born with a particle physicist, you see? And you are not worried, you are already Higgs. By birth, God has given you a particle detector. You should be curious to understand what other detector you can make it, right? Yes or no? But nobody want to do particle physics here. Yes or no? If you want to be a computer scientist, if I give a computer, you use computer to enhance your skill. But that computer was purchased by your father, so you care about father's money, right? God has given a IGNOU, it's free of cost, who cares? Yes or no? You use so much to be a computer science, you damage at the age of 15, 16, you need a lens. It's a free of cost detector, no? Yes or no? So we don't understand the value of free of cost, how expensive it is. Okay? So everybody is one of us. Like I am a particle physicist, you are also particle physicist, you have a detector, right? All right? So you are not different from me, okay? Together we can study particle physics now, okay? Yes or no? Okay. So we need detector which will detect also photon, electron, photon is a particle, right? So we have two detector, one accelerator. Be positive, open mind. Now you are particle physicist. You should be able to ask question. Open your mouth. Okay. Do you see here? How many detector? How many accelerator? Why? Why? If you don't ask question, I will ask question. You ask me or I will ask. It's your choice. Why? Why means what? God gave me 2 eyes. Do I ask God? God could have given 3 eyes also. It's just God decision. 2 detector. You might have decided 2 detector. How do I know?
Verify if one of them, like by chance picks up something, it might be wrong in the other.
You see? So that is why God has given 2 eyes. You see, this is logic. In one eye see this, you verify this eye. Okay. Correct. Yes or no? You don't do this, but you can do. If you have some problem, you close one eye, see, and this eye, okay, so it's fine. Always you verify too. How beautifully God has given this character, you have to have at least 2 to verify, not 1. So we use same thing what we learned from the God, okay? Nothing else actually. It is not a scientific choice, I just learned from myself actually, okay? Anyway, this is 2. Okay? Yes?
Sir, like how do we detect Higgs boson? Like if there's a particle and like when you find it, like
Yeah,
it's
you are
formed in
going
the
too fast.
accelerator.
Higgs boson will come later.
No, sir. Like how do you, even if you get it, how do you detect that it's there?
How do I detect?
That it's there. Like you found it. Like what distinguishes it? Like that you can measure. That we can
You want to stop my class here? It looks like I will answer and then my class is over. If you go to a movie, you watch movie, finally you understand what it is, but initially you said, what movie tells, tell me actually, I am done with this. Summary of the movie, tell me I am done with the movie. Interesting part is you have to be patient to watch the movie also. Yes or no? But you are asking, tell me the, I'll tell them, that's the excitement, you have to hold it. Yes? Okay.
Sir, if you have two detectors just to verify, why do we have two different detectors? Why can't we have like Atlas 1 and Atlas 2? Why do we have Atlas and then CMS separately?
Okay, that's what is asking you understand. Your friend should answer now. Because all are particle physics, I am not only one of them. Feel it? You see, he is tell it. Huh? Different agency, exactly. What is your name?
Sir, Adivid.
What is your name? What is your name? Why different name? Different agency has created. That's it.
But sir, we are not the same, no sir.
Huh?
We are not the same.
Name is different. Purpose is. You verify. Exactly. Is it okay? All answer you know actually. Because if I ask question, you will ask random questions. I want to make sure that your random questions can be answered by your random friends. If it is spillover, I will answer. No? Otherwise, I will be answering random questions as interesting question will be left over. Okay? Everything you can understand. Just believe you are a particle physicist. You tell your mind, I am not a 12th standard is I am with a particle physics, I have a particle detector, I didn't realize on that day. Today I realize I have a detector, I should be behave like a particle. That's it. And you will be particle physicist. Just tell you are particle physicist. Over. Yes or no? We are trying, sir, actually. Okay. How do I do that? If I want to understand the thing here, I am sitting here, I can look back here. Think, very interesting question here. How do I find Higgs? He asked also. Higgs was here actually when universe was 10 to the minus 14 second old. I am sitting here 12 billion years away from the point. How do I say it? I can look at eye, my detector will not go, my detector has a range. Even I look at her, I cannot look beyond few kilometers. But how do I go there? So my eye will fail. So my detector will not go. God said, that detector capability, this, you don't need to look at me when I created universe. That should inspire you to build a detector. Don't use the detector I gave you, otherwise everybody will be same. You have to use this. Now, LHC, Large Hadron Collider, why do we need? Recreates the condition. Recreates, very important. What was here happening to the universe, when universe was age of 10 to the minus 14 second, Large Hadron Collider, let me finish my sentence, okay? Large Hadron Collider is so excited, you say, stop, even word by word we will ask question, okay? We will not allow you to go to second word also. So you are detecting too fast actually. Once I told you particle, you detect too fast. Existed about 10 to the minus 12 second after the Big Bang. That means I need Large Hadron Collider which will recreate the condition which was there. If I recreate the condition, whatever happened to universe there, it will happen now also. That is why I need Large Hadron Collider. Is it clear? Okay, question.
Sir, how did we calculate that after Big Bang in 10 raised to power minus 12 seconds, there would have been bosons if they were there?
Okay, that comes from my last class. Last class, he didn't ask this question because I didn't tell he has a detector and need particle physics. Today I told immediately, he got, I missed this question, you see. Yesterday you are supposed to ask this question.
No, sir, I thought about it.
You see?
I couldn't find it, so I asked.
Because today you realize you are particle physicist, I can ask the question, you see. That is exactly. If you look at the picture I showed, this picture, 3 lines were there actually. One of them was temperature. To measure the time, we just look at the temperature. Universe was very hot initially, okay. The temperature you can calculate. If you contract the universe, volume will decrease, this is simple. Then mass will increase, all will be in the thermal energy, is a temperature. So if you can figure out when universe was 1 second, what was the temperature, now the temperature is what? Universe temperature is? What is the temperature? Nobody knows. What is the temperature? Hurry. Yes, he knows.
So the graph yesterday said 2.7 Kelvin.
Exactly. You see, he likes the graph 2.7 Kelvin. You see, very good detector. He used very nicely. He's sitting there, same eye like you, detect very fast. You see, use his eye particularly efficiently. Okay, you understand? The universe is cooling down because of expansion. Okay, is it okay? But we are getting more heat in the summer. We say summer is getting hotter, average temperature of the earth is increasing, but same time I am telling you the universe is cooling down. Is it contradiction or same also? Okay. You understand my question? Yeah. Universe is cooling down. We are worried about global warming. And we are doing research on that, right? It's okay. If you understand, no problem. It's okay?
Sir?
Yes.
Sir,
Yes.
last class you told that the conditions in the LHC was at the time when the universe was 10 to the power minus 14 seconds old. So I just want to clarify if it was 10 to the power
14,
minus
14 minus 14 minus 20, 12 minus 16 is similar range actually.
Okay.
Okay, you don't exactly, this is a band actually, if you see the band, okay, no, we don't point a number like this, it's just a band. If you look at the band structure, yes.
Sir, before the Big Bang, whatever had caused the Big Bang would have also had a considerable amount of mass, right? So do we have any evidence to study what happened before the Big Bang? And would studying that kind of tell us anything significant to understand the universe now?
I could not get, before the Big Bang.
Yes, sir. So before the Big Bang, whatever caused it must have also had a considerable amount of mass, right?
Yes.
So do we have any evidence of what happened before that? And will studying that tell us anything significant?
You want to answer? No, don't answer, I will answer, because finally she asked question from yesterday, okay? Today she realized she is a particle physicist asking question, I should answer, okay? So, yesterday if you realize, I told matter is created after 10 to the power minus 14 second, when Higgs field was eaten by this massless particle. Before that there was no mass actually. If you look at the graph, that is where, if you look this expansion yesterday, I told 10 to the minus 44 second. LHC gives me 10 to the minus 14 second. I have to go 10 to the minus 44 second when universe was, it's very tough. That is where we realized that gravity was too strong at that time. If you realize, it is not the strong force, it is important. If you put whole universe to a point, whole mass will be in one place. It is the gravity who holds it. And something happened and gravity becomes weak. That is why expansion is so fast. That is why it is called expansion of universe, which we do not understand what the mechanism yet. Within 10 to the power minus 14 to 10 to the power minus 16, you see even not 1 second. The expansion so fast, we don't understand what the mechanism is. What was holding that, we think is the gravity. And gravity becomes so weak, that is why this whole galaxies are moving away, because gravity is weaker. But if gravity is strong, everything will collapse. That is why we are not able to understand gravity in standard model, because gravity was playing a role when universe was minus 10 to the minus 44 second. If experimentally I have to understand gravity, I have to create accelerator which will take me to not 10 to the power minus 12 second, minus 44 second. And that means if you are really want to do physics, you can calculate acceleration. How do you do the particle, charge particle using your electric field? What is the field is required? And if you see, we need accelerator which will be look like not our earth is not good enough. So that is why gravity is still a elusive thing to understand, because experimental we cannot prove. There are theory which explains how gravity, like string theory you might heard actually. No, nobody can prove it is right or wrong, because no experiment can be done to prove string theory. So nothing until unless experimentally proven, we don't believe. That is why gravity is very difficult to understand at this point. The theory which explains this is also very challenging, because we do not have a mechanism to do the experiment. And gravity was playing the role when universe was 10 to the minus 44 second. And I do not have a machinery which will recreate the condition 10 to the minus 44. We are just minus 14, minus 15. See how difficult it is. That is why the challenge for all of you to create an accelerator, tabletop accelerator, let us say now it is going to laser accelerator. How quickly you can energize a particle with a small distance. That is why the technology breakthrough is required. My generation will not touch that part, because we don't have technology. So if you want to understand this expansion part, it is beyond our limitation in the next 30 years. New generation has to come with the new idea and make the innovation. That's the challenge for all of you. Is it clear? Very interesting question, you see. Exactly. Same. Recreate the condition same.
So how the collider will handle that energy and temperature inside it?
Very. So I think I should have created only 20 slides actually. I thought the student will not ask any question. So I will be the person who will be now. Yeah, go ahead. It's your class, it's not my class. Go.
Sir, if all of matter and everything in the universe which is there currently now is confined to that one point, wouldn't matter and antimatter annihilated each other to just give pure energy at that point? There would not be any matter in that one point.
You see, this is a very interesting question. Okay. Think about whatever matter, antimatter, leave it. If we collapse this room, what will happen to you and him? You'll be one. Yes or no? You don't have a choice.
How do we ensure that LHC recreates the same condition as that existed at 10 power minus 12?
Done actually, don't worry, it's a physics. It's a physics. Equation I can tell you and you can calculate and you can, that's a verifiable, no problem. Okay.
Sir, yesterday Balakrishnan sir told us that currently at LHC they're reaching speeds of 0.999 times the speed of light.
Coming. My
Yes,
slide
sir,
is
yeah.
there.
So like how do we advance more than that? Because the limit is at the speed of light, right? So it's like how do we advance it?
We'll come to that. Okay.
How do you even recreate some such complex situations like the Big Bang, like 10 power minus 12 seconds?
Do you think you are not complex?
Yes.
I can
But
recreate.
I didn't recreate me, right?
I recreated. I told you to recreate dark matter. That's your challenge. My challenge was recreating that.
No, I am asking, LHC is recreating such a situation. How do you do that?
Wait. This is. That means nobody is listening to anybody's answer actually. Now I realize everybody wants to ask question. Your friend also asks question. Now there is a competition of who can ask question. We should not go to that. The question was already answered by them. When somebody say how to recreate, I said temperature. Yes or no? See.
I'm not saying.
Okay, I understand. How it recreate the same temperature? Okay. I have to go to the next slide. No, because I just showed the picture of I just showed this picture. I don't know what is I written there. It's just a trailer. Movie didn't start, and you ask actually how hero shoot something. Okay, no problem. Keep quiet little bit, digest a bit. Okay. Then you ask question. Okay. We have the Hubble Space Telescope. That's also being used to look into the how the universe is. Okay. You can search, and Hubble telescope is kind of our eye. Not looking at the photon but microwave radiation. This is also kind of a detector, but for different particle. Can only see as far back as about 1 to 2 billion years after the Big Bang. I am not even going to 1 second. I have to go 10 to the, if I have other way, I can do that. So I am trying many different ways. Double map experiment that studies the cosmic microwave background. One of you may be interested to do research in that area. This observes only 300,000 years after the Big Bang. That is the limitation of. Out of 3 ways, only LHC takes us to that. How? We can discuss. Okay. Now we understand why do we need large hadron. Is it clear? How it does? That's our job actually. Okay. But we know this. So I have chosen this because I am an experimental particle physics. If you are interested to that, you will go to this area of research. If you are interested to this, that is how it's been distributed. Why do we need so long to do the LHC? Why? Because this is one of the theory. John Ellis, these people in 1975, when even I was not born, people thought about Higgs and creating that. What he says, this is theorist. They should point a direction. They are not sure. We should perhaps finish with apology and a caution. We apologize to experimentalists. Theorists are apologizing to why? For having no idea what is the mass of Higgs. The Higgs mechanism never tells the mass of Higgs. This is a first time a theorist tells, I can predict, I cannot tell you the mass. And that is the first question mark and biggest question mark. Unlike the case with charm meson or charm quark, mass is predicted. And for not being sure, it coupling to the other particle. Its coupling is not understood also. How the mass, how much mass, because Higgs mass is very important. Except that they are probably all very small. For this reason, we do not want to encourage big experimental search in Higgs boson. If you are a theoretical community, which is 50% of the world, they do not support, no government will pay you $1 billion to see. When around 90s, when no experiment found, all theorists figure out this is what we also want, then all the world body encourage their comment that this is the question even we also want. Let's invest money, billions of dollars is worth. That is where big experiment starts. It's a big question becomes. Okay. Why it did not start 75? Because even theorists were not taking risk to give a support saying that we can spend for a question billions of dollars. It's not million, billions of dollars. Accelerator cost $10 billion. You can think of billion means you should understand how much money is being invested in Switzerland and how important question. It's just a one question. For you, it is one question. Why? It doesn't give you any money. But its question is billions of dollar question. You should be able to put your hand saying that I was part of this mission. That's it. Okay. Okay. By mid-90s, Higgs boson was considered the most critical particle to be found experiment. Everybody asked question, we want Higgs at any cost. Take the money, do the experiment. Tell me Higgs. Okay. Now, Large Hadron Collider, this comes how your question will be answered. Now your physics now, okay. Unit and numbers, interesting. 1 electron volt in kg, you know all in kg, right? But we talk about EV, MEV, GeV, right? So you should know the conversion. Proton mass 1 GeV, 10 to the minus 27 kg. So when you go 10 to the minus 26, it doesn't look good. So we have converted such a that you don't worry about. We go to the GeV. Electron mass 10 to the minus 30 kg, but 0.5 MeV. Sun mass 10 to the 30 kg. Higgs mass 10 to the minus 25 kg. Higgs mass is predicted 100 to 600 GeV. This is the range the experiment should search, because theory thing is there. It doesn't say 100, it doesn't say 125, it says 100 to 600, wherever it is I don't care, you can find, okay. You don't have to write actually, this is Google search will tell you everything, okay. Just listen, yeah, go ahead.
So we are taking approximations here for the mass, right?
Huh?
We are taking approximations here. Why are we?
This one?
Like mass of electron, mass of proton, all that. In kgs.
This one or this unit?
The mass, sir.
Unit.
In kgs, what we have written, the numbers, the numerical value.
This is actually, if you go to the number 900 something, I just put one, don't worry actually. It doesn't change anything. Look at GeV to kg, okay. Unit conversion. I said unit and numbers. So conversion is a factor, okay. Okay. We will mostly use GeV in our discussion, and if you want kg, you convert to GeV to kg, that is what I said, okay. E is equal to mc square, okay. How do we go there actually? This is your question, understand. We have to collide 2 proton with, let's say 4 TeV, tera electron volt. You can figure out now conversion, I don't have to do. Total energy will be available 8 tera electron volt. Accelerator, what it does? You can recreate the new particle if the mass is less than total energy available. So that is how you design the accelerator, okay. Actual interaction occur between quark and gluons, because that is what the building block of your proton. If you proton-proton collision happen, the proton will not collide, proton will collapse. What they will see, this quark, they do whatever, and whatever we get actually out of that. Most particle we create live only for short fraction of a second. That each particle you see has the lifetime, okay. Electron lifetime is stays forever. Proton lifetime is, what is proton lifetime? Stays forever. The proton decays, will decay, collapse. Understand? Proton is a particle. The day proton decays, you will decay. Done. Okay. Neutron decays. Yes or no? Yes. If neutron decays, you should decay also, because you are made of nucleus. If neutron decays, then you should collapse. No, you are not collapsing. Why? Huh? It's not decaying. You see, he says it's not decaying because I exist. No. Neutron decays. If you pull out a neutron from the nucleus, it will decay. If it is inside nucleus, it doesn't decay. Okay. That is why we are here. That is, if you pull out a neutron, that will decay to proton with a beta particle, beta decay. You might have heard. Okay. This is how it happens actually. Proton, proton, quark. Then this is the energy available, and you can create a new particle. Okay. It's fine.
Sir, we know that if you have two protons and you collide them, you will get these particles. Do we know exactly how the particles are getting with the actual
Exactly,
conversion?
everything we know.
Sir, how, sir?
You have to pass +2, then BSc, MSc, join PhD, you'll know. I mean, if you want to test tea, chai, you want to drink tea and you are 1 year old, you ask your papa, give me the tea. He said, no, you have to 5-year-old, at least 4-year-old, which will be very hot. You will cry more actually. You will not enjoy. No, give me the tea. No. Is it okay? Why you are not given hot tea at the age of 1 year? You ask your parents, why you didn't give tea? I am enjoying coffee now, why you did not give? Say, Ray, you cannot. Since I am like this, I cannot give you the hot tea when you cannot digest also. You may throw, I don't like it. My intention is not to hate tea. You see, you go to the downside, you drink tea. If that happened and you say, I hate tea, why? I was 1 year, my father gave me the tea, I really hate my life. What is this? Yes or no? I am here to encourage and make your taste better or worse? Better, right? Okay. Sometimes if I don't give you, don't think I don't want to give you. Okay? So this is what Large Hadron Collider looks. Okay, go ahead.
When we like collide any two particles, can we predict what's going to be created?
Yes.
Like
that is what we know. Standard model is beautiful theory, I told you. Everything is except gravity. You ask, it's just like a machine, Google search like. You do PhD, you will see actually beautifully, you will predict actually. You will calculate everything. It's a math actually, nothing to do with. Okay? That you should understand is there. Okay? Otherwise you cannot do anything. Somewhere you have to believe that I came through the gate. No, I didn't fly here. That is a door, it is opening at the, if you don't know this door opens, yes, sir, how did you come inside? I cannot believe. You have to come, open the door, then you believe. And that to do, you need another 5 years. Okay? So, this is. Okay, very good question. You see, your friend is asking, you should ask your friend. They can answer actually. He says, if what will happen is proton hitting the wall. What will happen? This is a door. What happen if you go hit the wall? Do you think you would? Why can't you hit the wall? Why? Because you know. Yes or no?
Excuse me, sir.
He enjoyed now. Huh?
You know the diagram that you show the diagram in the previous slide. Could you explain what E and E?
E is electron, E bar is positron.
How will the electrons?
Finally, you want me to slow more down actually. You want me to slow down completely. All people will say, well, we don't care how it is because that comes later. This is, you are excited, his job is done for me actually. Once you are excited, you will get the answer actually. Nobody can stop you getting the answer. Or you will send me a mail saying that I saw your email ID, you answer me. That only 1 or 2. Okay. This is a accelerator in border of Switzerland and France. Okay. Then collision happen here, CMS detector, Atlas detector. There is a Alice detector which looks for the quark-gluon plasma. Huh? Huh? Collision energy, that's it. Center of mass energy, which I told, root S is total energy, 80.
Sir, why are we only colliding protons?
is another. You see, you really curious, okay? We need really, why do we collide proton? What do you want to collide, tell me? According to you, what we should collide? Definitely. Wait. Neutron is neutral. Through my physics so far, up to 12th, 11th, and I can only energize a charged particle. That is what electric field I know. How do you energize, move a neutron, tell me? Neutron. You invent something and become famous. That's a Nobel Prize winning problem. If you can have a mechanism, accelerate a neutron and like a proton, that discovery will give a Nobel Prize. It's okay. It's a Nobel Prize question, and whether you will succeed or not, that's your choice.
Sir, what if we shoot an electron at a proton?
Electron, yes, there actually, no problem. But that will not give you 10 to minus 12 second.
Then what will that give?
That is coming another in US, another experiment. You will Google search will find. Purpose is different. If you can do electron proton, purpose is different. Electron positron, purpose is different. In Japan, there is another accelerator. KEK, you go, there is an electron positron collider. You go to Fermilab, they did proton antiproton, purpose is different. Okay? All are charged particle. Whenever you do, it's a charge, because we know how to accelerate a charged particle. We know how to control the trajectory of a charged particle using the which field? Magnetic field. That is where your Lorentz force plays a major role. Okay?
Sir, what if we do electron-electron collision? Will they just bounce off, or will something happen?
You do the experiment, no. You have a life. Why do you want all the answer from me? You spend your life, decide I want to do electron-electron collider, do the research on that, discover something, make it. What is the purpose of this lecture? Create the excitement inside you. Don't have to answer everything. There are so many unanswered questions which you are supposed to take up in your future. If that compels you, okay? And even your parents, you go to computer science and no, I want to do this. Why? This professor told me, it challenged me. No, I want to show this. That's it. You become a mad person starting from now. I want to do this. Yes or no? True or not? All of you are kind of mad, right? Yes or no? Yes or no? Yes. Of course, actually, if I tell you what is your mission success, you see? Why don't you go, no, I like this, I will do this, I will do this. Are you mad? No, I want to do this. Mad means looking your goal and your dead end, that is what I want to do. Right? Sir, we thought actually we are the smartest guy among all this and you told us I'm mad. Okay, that doesn't matter to us actually. Our mission will not change. Right? Oh, comes to interesting part. Listen, 2 minutes. That is more interesting. Come to here. This person, he created an accelerator. This is the accelerator you can see. Only 80 keV. He got Nobel Prize. Nobel Prize. Understand? Why? Because he invented a technology where you can do the circular motion of the. Before it, people thought only accelerate by linearly. If you accelerate a charged particle, you put the electric field, then you accelerate. But he said, oh, why do you go so long? You can do the circulate also. And that gave the Nobel Prize. It's just a breakthrough in the technology. You should aim for a Nobel Prize or not? No, sir, actually, we want engineering, at least if I enter to this place, after a year, I'll be very happy. That's my mission success, right? Nobel Prize, we Nobel Prize, nobody. I cannot be that mad, right? We are mad, but we are not that mad. So how do you do that? Acceleration is very simple. Now you understand battery. See, that's your physics. F is equal to QE. You know that. You know, right? Newton, you know. Acceleration, you know. This is very simple. Look, this is what we use in the accelerator. That is why I say you are born as a particle physicist. By 12th standard, you should sound, I can do the Higgs, whatever sound. Only I cannot fly, that's a different, but I have the capability, okay? So that is how you do the acceleration. How do you hold the trajectory of the particle? You cannot accelerate. That is your question. Why it's not hitting? Magnetic field is there, okay, to hold the trajectory. Otherwise, if you fail, it will hit you, okay? To do that, this is also Fiji question or your IIT JEE question. You have this curve path, then you know that centripetal force mv square by r, you know this is due to BBQ, then you can get the whatever you want, the radius of curvature, and this is how. So this is still your, so this is what we use in the accelerator, not really big, okay. This is what the accelerator inside looks like. You didn't go to Switzerland, doesn't matter. I have been to there, I was part of the team working there. So this is the accelerator underground. This is the dipole magnet, 2007, I was there. What is the interesting question? The energy is 80 million times the what Berkeley did. 80 million times we have increased the capability. More than 8 billion years spent for the accelerator. Only is what? Okay. It took more than 15 years. Mission should be long term. Okay. Interesting question for you. Read here, he will ask another question. After I go to next lecture, I want to ask question. So 30,000 tons of 8.4 Tesla dipole magnets are there, cool to 1.9 Kelvin. 96 tons of liquid helium is stored there. It's the coldest place on earth. Energy is megajoule, which is equivalent to 15 kilo of Swiss chocolate, because it's Switzerland famous for the chocolate, and chocolate is written what is the calorie. There are challenges, is a lot, okay. You don't have to worry about this. This is the 2 detector, okay. This is the biggest detector, it's the heaviest detector, and this is how many countries are in one experiment is Atlas. India is part of CMS. India is also member of the one of the collaborators which does this. And this is how many age group people we just look at. We make sure that young people come to the system and they see it. You see, and mostly 25 to 29 more energetic people are interested to do this, and you can see it's nice. CMS is heavier than the Eiffel Tower, okay. This is in the size. Okay. This is how you detect the particle, okay. The particle you detect, your photon you see, we detect through eye. We have a special detector who does the photon. We know the charged particle, which we use this magnet to bend, and from bending we can get the momentum. mv square by r is equal to bvq. If you equate, you will get the momentum in terms of magnetic field and the radius of curvature, okay. So you can do this. We built the detector. I was part of this team which built this one of the special detector here, which is called silicon pixel detector. So just to test you, this is where we test one of the detector before we install, as if you have to make sure your detector works, okay. Every stage you have to be very careful. Anywhere mistake, it can collapse whole experiment. So you have to be very super careful planning has to be superpower. So everything has to be taken care of. Okay. Just to tell you one unexpected story, what happened at that time. This detector is very special and very expensive also. We don't have second detector. And if one experiment fails, delay, other experiment has to delay. As you know, two of them should discover anything together. Otherwise, it's a false alarm. That is why we have two detectors. So when we were doing that, this detector, we as a part of the team member, we say we should test it before we install into the system. But project leader told, no, I cannot take the risk. If it breaks, I will take the responsibility of whole CERN experiment will delay, because we delay by a detector, no, everything has to go. But we said, if it fails in the system, what will do? You have to open, it's very difficult. Finally, he allowed one part of the detector to be tested. We have a barrel, two end cap. One of the end cap, he said, you can take a risk. Okay, barrel don't touch. Why? With barrel we can do physics also, Higgs physics. So it's protected. When we did actually everything, when you power on the detector, detector didn't power on. Everything was proven and you turn on the power, detector doesn't listen. What do you do? Then it has gone to the whole collaboration that pixel detector doesn't work. Right? Without pixel, no Higgs. Then we are not prepared for that unexpected problem, because it was planned and all design, everything correct actually. Since this detector has to be sitting close to the collision point, radiation is too high. So in the radiation environment, if you put anything, it will damage, radiation damage, because of knockout so much electron. That is why we put the detector to run at minus 20 degrees centigrade, which should be cooled down to reduce the radiation effect. Electron is also we designed to run at minus 20. But it doesn't work actually. So what happened actually, you can see, just like everything is done by the physicists, you can see what is sitting here. Because you have to do, all physicists know about. What we did actually, we realized that this detector doesn't work, but we have to find out, and we thought, why don't we do some warm up to the electronics? Nobody told us. We have to do our own way. We cannot ask outsider give a solution, because they don't know the solution. You have to find a solution within the team, because it is not you can outsource and they will give the solution. And this is a question which nobody knows how to answer. So you can have this kind of problem in your future also, where you have to find a solution right away. You don't have a time also. And that makes you success or failure. So what we realized, it was difficult to understand the behavior of optical signals, which we designed to run minus 20 degree. So what is done? We don't know. There is an optical board here. We put a wrap here, kept on tape. When you turn on, the electrons will radiate, generate the heat also. This is like a blanket. You use your own heat when you are outside very cold. What do? You use your shirt to use your own heat to warm it up. So this is what exactly we have done. It is just simple thing. When you did this, detector start turning on. Then we realized that opto board, which is designed to run at minus 20 degree, is not running. It needs normal temperature of 5 degree. Now you see, you have designed all the system to run at minus 20, and you realize one of the electrons doesn't run. What do? You have to redesign such a way that detector runs at minus 20, electron runs at normal temperature. You cannot change the design also. So what we have done actually, immediately we make a team which will create a heating system. You cooled minus 20, but heating system will heat the electronics. That is how the Atlas was commissioned and run. This is the detector, but once we see this, by the time we run the detector, if you see 2011, 96% of the channel, means electronics channel, was alive. You can see regularly in the live. And how many electronics channels we had here? 80 million. 80 million channel you have to read out every second, think this is alive or not. It's huge technological improvement has to be done. You cannot just say that your detector is running. Complexity is huge, but we are able to manage. So this is where, before Peter Higgs came, before you close the door, he was our spokesperson. Okay, before you close, Peter Higgs is excited. You will find my Higgs. No, so he came and see. Okay, good luck. Before we do that, it's me who would work for this. This is the Atlas core. This is the beam pipe. Now I cannot touch that part because it's a radiation area, and I also say goodbye to my detector also. It's done. This is not all. You may be interested in this area, which you become the data science or computer engineer. That is where we also do a lot. Okay. It also gives you an opportunity to be computer scientists work in this experiment also. Okay. With this solution with the grid computing, now whole world knows we are part of the grid connected to the system, and we are ready to start the experiment. Experiment result, I think we should go to the, this is not for you, this is Peter Higgs again. This is what the excitement you see. The first time when a PP event came, all our physicists sitting in the control room, they are excited that their detector can see some signal from the proton, which was 15 years of accelerator, 10 years, 15 years of the detector. Finally, we see everything was. What is the joy? You see, as if they find their lifetime achievement. Same room, I am here. You see the first event, how it looks like. And when the flash event happened, we said pixel detect should be off, because if something happened, it may burn also. You see, we have to be curious. You can see middle there is nothing actually, because you turn off the pixel detector. Only the outside detector was on to see that behavior of the accelerator is correct. You have to be very careful. Slowly we learn and we turn on our other detector. This is beautiful picture. First proton-proton collision, you see two. When you have bunch of proton coming here, bunch of proton coming, you can see exactly two protons are colliding. Okay. But later it becomes 26. In one collision, you have a 26 event is created. Now if you go, see it's 150. We expect 250. If 250 collision happens, you have to separate them within 25 nano. It's very complex computing also. So you see all the complexities here. Wherever you see it is connected to. So you can find a way, if you are interested, look at this. So just to see road map, just to show you, this is where the Higgs comes. Okay. In 2011, 7 TV, you can see small spike here. You can say there is nothing. There is spike here, spike here. It is in 2011, 7 TV, we are supposed to run on 14 TV. When we showed this, theoretical community in the world, they said Higgs is observed already and published paper like anything. We said this is not observation, we said some excess is seen. And later we see exactly same place. This is the discovery. That makes you, both experiment finds same place. Pick here, CMS, pick here, exactly. Both experiments should find at the same place. Okay, 126, now it's 125. So other decay mode also they found. This is one of the Atlas Higgs event going to 4 electron. And this is what it says actually, how you convince the world that you discovered, because you have to tell that your probability of statistical fluctuation is less than 1 in 100 billion, that you cannot say 100%. Probability always goes like this. At this point, we are pretty sure this is the signal, and This is what 2 experiment confirmed, then the Nobel Prize comes. That's the end of the story. Okay. Peter Higgs and Fabiola, who is now CERN director, she was spokesperson of Atlas. So, okay. This is the roadmap to how we discover Higgs, which is responsible for giving the mass. Question.
Yes, sir. In one of the previous slides, like long ago. Yes, sir. This one, sir. Yes, sir. Here, why are only 2 lines in yellow color?
Which one?
There are 2 lines in yellow color. Rest everything are grayish. Why are those 2 lines? Okay.
This yellow?
Yes, sir.
This yellow, na? This yellow.
Yes.
So these are the charged particle. Okay. In detector tells this yellow lines 2 are muon particle. Detector can detect muon, electron. This 2 muon is coming from a same point. You see, that means one particle is decaying to 2 muon. And if we calculate the mass using the 2 muons momentum and energy, it comes out to be a G boson, which we know G boson is what? Weak force, no? And it's beautiful, no? It is created, it decays to 2 muon, detector sees 2 muon, you make a pointing to whether they are coming from same point, means mother is same, then you see yes, correct, actually you see 1 point, then you put the mass, calculate, it is 90 GeV, which is your G mass, G. Same way Higgs, 2 photon, get the mass, if it's 125 GeV, Higgs. If it's not, it will be 200 GeV, 300 GeV. This is how we find the mother through the daughter. Go ahead.
Sir, how did we accelerate the proton to 99.99% of C?
That accelerator physics is simple actually. You can accelerate anything you want. You just
how
increase.
Did we accelerate that much?
If you know the strength of the field, you can calculate from this mv square wire actually the velocity. That's it. V is a c at this point. You increase the speed of light and you can see the bend. This equation is there actually. You can figure out. If you put the magnetic field strength, everything, you can see that how, that's it. So that is where how speed you can do it depends on the strength of the magnet. Electric field will accelerate, but bending when you do know what happens, this goes slightly beyond you, that charged particle when it bend, they radiate the energy, it's like a photon, they lose the energy also. It is not like same energy they can keep it. So you will have a compensation, that is why you hit the limit, that whatever they are losing you are putting into the system, like proton is accelerating, they are losing the energy, then you say okay, I am saturating now, I cannot go, I need a high field, and when the field is high, strength would be high to keep in the track. Yes or no? It's a racing car kind of thing, okay? Done? Go ahead.
Sir, has there been any discovery from the LHC or any other particle accelerator which has not been explained by the theory so far?
No, we were looking for actually beyond standard model, and we are really looking, if we find that could be the Nobel Prize winning. Now we are hitting that also. We should find beyond standard model. That is the main focus of the world now. After Higgs, where is the new physics comes, and the theorists, they are working hard, giving lot of theory, but experiment should find no. So experiment find means that is what we are focusing on. If we find, this will be another joy for the next 30 years of celebration to work, and we are working on that actually. So far, no. Okay.